Alright, so now I want to sort of make a continuation off of the last video I made by sort of illustrating this concept of the vector being what's called invariant under rotation. That is basically fancy talk for no matter how I rotated that coordinate system that I showed you, no matter what way I could have rotated that x and y axis arrangement, that vector was never going to change. And you knew that because I didn't draw another vector, I didn't change it or anything, but you can use a of x and a of y, the formulas for a of x and a of y, as well as a of x prime and a of y prime, to really demonstrate the fact that the magnitude of the vector, and therefore the sort of real identity of the vector, has not changed no matter what rotation of the coordinate system I did. So in order to illustrate that, I'll quickly jot down for you, just to refresh your memory, what the original a of x, the formulas for a of x minus and a of y. Sine of theta in terms of a of x prime and a of y prime. The formulas for a of x and a of y in terms of a of x prime and a of y prime. Theta, of course, being the angle at which the coordinate system was rotated. Just make sure I'm right. Okay. So now what I really want to show is that the vector is invariant under rotation. And what that means, and I'll clear up the space over here since that's no longer needed. Try not to erase what's boxed up. And yeah, see, because the brush size is very big, try to make sure that I don't erase what I need. Right, now this idea of invariant under rotation basically means that the following has to be true. What has to be true is that a of x prime plus a of y prime, a of x prime squared plus a of y prime squared is equal to a of x squared plus a of y squared. Therefore, the vector has never changed because the magnitude is always the same. The way that I can show this to you is actually quite simple. If I take this and I plug it in here, and I take this and I plug it into here, what I will get is a formula. I will get this squared. I kind of just don't want to show too much of the algebra because I'm assuming that's overkill. I'm assuming that you are perfectly fine at doing the square of this and the square of this. Okay, so this is the expression that I got from doing this squared. And that's the expression that I get from doing this squared. Now what happens here is that this conveniently becomes 1, because cosine squared plus sine squared is 1. And the same thing occurs here. Therefore, this whole thing, which was a of x squared, right? This was a of x prime squared, and that was a of y prime squared. Becomes, right, because these go away, so this whole expression becomes a of x squared plus a of y squared. And therefore, we prove something which intuitively is very obvious. But it's nice to have this sort of qualitative, or I guess quantitative, proof to show that the vector truly hasn't changed under these rotations.